So we have this circuit here. We've got a battery of 5 different resistors in this sort of arrangement. And our goal here ideally is to figure out all the current everywhere and all of the voltages everywhere. So we can figure out more information as needed from that. And to begin with, I find it very useful to think of this in terms of how many different currents we have to consider. So if you just take a look at current, how many different currents would you expect to see here? Like if you just measured the current everywhere, how many different values would you expect to get? Just one for the whole thing? When would, I mean, we often expect same current everywhere along a certain path because of the whole idea of conservation of current. But the thing is, if you follow a path, like let's say you start here and you just go along this path and you continue along this path and you continue along this path. The thing is, you then hit a junction. What happens to current when you hit a junction and you have several different directions you can go? Yeah, the current's going to split. So we're going to have the current through the battery here. And I find that's a useful starting point. Anytime you've got just a circuit with just one battery in it, start by looking at the battery or the section of the path that contains the battery. So we have a path that includes the battery. That path has a certain current. We usually call that I sub 0. So I sub 0 is the current in the current flowing through the battery itself. And we don't know what that is yet. We don't know how fast current is flowing in the section of wire that contains the battery. But we do know that resistor R1 and resistor R5 are going to have the same current because they're on that same path. In fact, we would say R5, the battery, and R1 are connected in what sort of way? If they're all just along the same path, what sort of connection do we call that?
Does that mean they're in a series?
Exactly. R1, R5, and the battery are in series with each other because they're all along one path with no junctions to split it. As soon as the current hits the junction, though, it's going to split. Current flowing inwards towards this junction splits into 2 different currents. So let's call those, let's say, R1 and R2. Sorry, I1 and I2. So we'll call this current here I2, or let's call that I1, and we don't know that current. But we do know that it's going to continue looping around. This current continues along this path until it meets up with the other current. Let's call that I2, which we also don't know. And then at this other junction, I1 and I2 meet and merge together to form I0 again. So it looks like there's going to be 3 different currents. There's the current through this path, the current through this path, and the current through this path, because the current I0 splits when it hits this junction. And those junctions are very important things to look for. Whenever current hits a junction, it's going to split. So at this junction, what can you say about how those 3 currents are going to be related to each other? If we've got current flowing in, current flowing out, yeah, I0 has to equal I1 plus I2. This is the junction rule. The junction rule says that the sum of all currents going into some region has to match the sum of all currents going out of that region. In the example I just drew, if you look at the current going in, the only current going in is I0. But the currents going out are I1 and I2. So the total current going in, I0, has to match the total current going out, I1 plus I2. So that's the information we get from the junction rule. Current 0 must equal current 1 plus current 2. And that tells us that if we know any two of those, we can immediately find the third. In theory, you can even apply the junction rule to points that aren't junctions. Like for instance, let's say this point right here, this corner. The junction rule would say that the current flowing in must equal the current flowing out. In other words, the current that passes through resistor R5 is the same as the current that passes through the battery. So the junction rule also implies the idea that along one single path with no junctions, the current has to be the same everywhere. But the current isn't the same everywhere in this entire circuit because there are some junctions where the current can split. Any questions on that current so far? So we don't know any of the currents yet, but we at least have labels for all of these currents. And to figure out what those currents are, there's several ways we can proceed here. One way is if we take a look at the loop rule by drawing out a loop, that is some path that starts and ends at the same point. For example, let's say we take a look at this loop. We might call this the left loop, for instance. In that loop, we're passing through a variety of different things. We're passing through a battery, a resistor, another resistor, and another resistor. And what do we know about the voltages of all of those things we're passing through? In a complete loop, what do we know about all the voltages? Yeah, those voltages all have to add up to equal 0. The loop rule, also known as Kirchhoff's voltage law, junction rule being Kirchhoff's current law, is that in any loop, the sum of all of the delta voltages has to add up to 0. And this is very similar in some ways to the cyclic process stuff from 7a, that if you go through a path that forms a complete loop and you get back to your starting point, any state function returns to its starting value. So if we take a look at, let's say, the point right before the battery that has some voltage, go through the battery, this resistor, this resistor, this resistor, you've gone through a bunch of changes in voltage, but you've returned to your starting point. So all the total change in voltage has to be 0 since you've returned to your starting voltage. In this case, we're passing through the battery. We're passing through resistor 1. We're passing through resistor 2, and we're passing through resistor 5. So all of those delta V's have to add up to 0. And you could fill in formulas for these. For instance, the voltage for the battery is just epsilon. And what's the voltage for any resistor? What's the usual delta V formula? Yeah, negative IR. For resistor 1, we know we've got current 0, so I0 times resistor 1, R1, and that should have a negative there. And likewise, delta V resistor 2. Resistor 2 is going to be negative I, but it's a different current. It's current I2 times resistance R2. And likewise, resistor 5 is going to be negative I0 times resistance R5. And we could fill in some values there. We know, for instance, that epsilon is 98 volts. We know R1 is 3 ohms. R2 is 8 ohms. R5 is 2 ohms. So that gives us an equation that could, in theory, be solved. We'd have 98 volts minus 3, and let's leave off the units for the moment. 98 minus 3 times I sub 0 minus 8 times I sub 2 minus 2 times I sub 0 equals 0. And we could combine like terms. 3I0 and 2I0 make 5I0. But even if we combine like terms, what's the problem here? Why can't we solve this right away? Yeah, we've got two unknown values. And if you got two unknown values, you're going to need more equations. You can address this by setting up another loop rule equation. Let's say you make the outer loop. So you'd have delta V from the battery plus delta V from resistor 1 plus delta V from resistor 3 plus delta V from resistor 4 plus delta V from resistor 5 equals 0. That would get you a second equation, also with two unknowns, but the unknowns would be I0 and I1. So there's really a total of three unknowns, which means you'd need three equations. Loop rule for the left loop rule for the outer loop, and we could also use the junction rule as the third equation. So one way of analyzing this circuit is setting up a system of three equations, three unknowns, and then solving for the three unknown currents. That is absolutely a possible way to do this, and it will get you the exact correct answer. The problem is setting up systems of equations can be a huge hassle to do. And there's easier ways to do this. So it's certainly possible you can solve this as a system of equations. And if you're familiar with systems of equations, I would recommend trying it out to see how it works. But let's take a look at a different way of doing this. Instead of setting up loop rule equations and trying to solve this as a system of several equations, several unknowns, let's see if we can get this down to just one equation, one unknown. And one way to do this is by simplifying the resistors. We've got this huge tangle of lots of different resistors here, but some of them can be combined together. For instance, what's a pair of resistors that could be easily combined together into just one big resistor? What are some resistors that are connected in a very identifiable way? Where it's very clear that they're in series or very clear that they're in parallel. One and five, yeah. How are 1 and 5 connected?
They're parallel.
1 and 5, how would we be able to decide whether they're parallel or series? Because it can sometimes be difficult to tell just from looking at it. But if you take a look at the actual meaning there, one of the most important things about series versus parallel is what has to be the same. If two resistors are in series, what has to be the same about them?
The current?
Right. They must have the same current because they're on the same path, because they're on the same path. Whereas in parallel, what has to be the same? If you got two resistors in parallel, they have to have the same what? Yeah, they've got to have the same voltage, specifically the same delta voltage. And that's ultimately because they're not on the same path. They're two paths or two or more paths that start at the same high voltage and end at the same low voltage. So parallel would be something like maybe you have a path that starts here and goes through a resistor and then continues. And also a path that starts here and goes through a resistor and then continues. So these two resistors are two paths that both start at the same high voltage point and both end at the same low voltage point. Since they start at the same point and end at the same point, we would say these two resistors are parallel. But for these two resistors, R1 and R2, they don't really start at the same point and end at the same point. Instead, it makes more sense to say they're on the same path. And we already established they have to have the same current because there's no junctions in between them. If you got current passing through R5, that same current has to pass through R1. And also thinking about this in terms of paths, if you imagine you're walking along the wire, if you're walking along the wire and cross over R5 and keep going, you have no choice but to cross over R1 also. R5 and R1 are on the same path, so they're in series. On the other hand, if you take a look at this circuit, this network I just drew, if you're walking along this path, you don't go through both of these resistors. You have the option of going through one of them or going through the other one. So parallel resistors are sort of mutually exclusive in that way. Any path you draw is going to go through one or the other, but not both. Whereas in series, any path you draw has to go through both of them or bypass both of them. So both of them or neither one. So that's one way you can check if they're in series or in parallel. 2 and 4 don't really have a connection in series or in parallel. 2 and 4 are definitely not in series with each other because passing through 2 doesn't guarantee you have to pass through 4. But also 2 and 4 don't start at the same point and end at the same point. You could say 2 and 4 end at the same point, but they don't start at the same point. Because 2 starts here, and 4 starts here. We can say 2 and 4 both end at the same point because of the points where they end are connected directly by wire. But 2 and 4 don't start at the same point because R3 is in the way. What we could say though, we could say that resistor 2 is in parallel with this entire path, the path that contains R3 and R4 together. So 2 is not in parallel with 4, 2 is not in parallel with 3 individually, but 2 is in parallel with 3 and 4 together. Any questions on that so far?
So if resistor 3 were not there, then resistor 2 and 4 would have the same current, correct?
Not same current, but same voltage. If so, we can say, for instance, that the difference in voltage from, let me mark a couple of points with the highlighter here. If we take a look at, for instance, this is, let's say, some high voltage, and this is some low voltage. And I'm marking this entire region because any points connected by wire are guaranteed to be at the same voltage. So this entire region is all at a single voltage. This blob up here is also at some other voltage. So resistor 2 is a transition from some high voltage to some low voltage. Resistors 3 and 4 together, this entire path also transitions from that same starting high voltage to that same ending low voltage. So resistors 3 and 4 together, that cluster is in parallel with resistor 2. We would say those are two parallel paths.
Okay, I think that makes sense. Thank you.
And it does take some getting used to. This idea of series and parallel is not immediately intuitive, and it can be sometimes difficult to tell just by looking at them. Are they in series? Are they in parallel? Are they neither one? Like, for instance, if you look at R2 and just R3, those are not in series, and they're also not in parallel. But R2 is in parallel with R3 and R4 together. And how would you say R3 and R4 are connected to each other? Yeah, R3 and R4 are in series because R3 and R4 are on the same path. If current is flowing through R3, that same current has to flow through R4 because they are on the same path. There's no other splits. There's nowhere else for the current to go. So R3 and R4 are definitely in series. R2 and R5, we can't really say R2 and R5 are in parallel or in series. R2 and R5 are definitely not on the same path because there's a junction between them where the current changes. But we also can't say R2 and R5 start and end at the same voltage. Because if you take a look at the voltages here, we do have this voltage that they have in common. So R2 and R5 both have the same voltage at this endpoint. But if you take a look at the other ends, R2 has some voltage at the other end, and R5 has a different voltage at the other end. So R2 and R5 both have the same voltage at this point, but if you look at the other end of R2 and the other end of R5, those are not the same voltage. They're not the same region of the circuit. So we can't really say R2 and R5 are different paths that start at the same point and end at the same point. They have different endpoints. So those are not in parallel and also not in series. Given the resistances, how do we find voltage at resistors? To figure out the voltages, it actually helps to find the current first, or some of the currents. Because we can figure out the voltage on the battery. We know the battery adds 98 volts. So we could say that the difference between, let me draw this in again. Let's say we call this region, if we say this region is a low voltage region because it's right before the battery, and let's name that. Let's just call that region 0 volts. And we could call it anything. There's no reason we have to call it 0 volts. It's just that 0 is a convenient baseline reference point. So let's call this corner 0 volts, and we'll measure everything else relative to that. The battery adds 98 volts. That's really all a battery does. A battery creates a constant difference between a low voltage zone on the negative side and a high voltage zone on the positive side. And the general notation, if it's not otherwise marked, is that the long bar represents high voltage and the short bar represents low voltage. So we're going to have high voltage on the other side. So this zone is going to be at 98 volts. And we can label that also. This region is 98 volts. And then after the resistor R1, a resistor causes a decrease in voltage. So we should expect this next zone to be a lower voltage. And let's label that as well. Let's say we call that this sort of light green. This region is going to be at some lower voltage. And it helps to imagine voltage sort of spreading out along wires, that if this point is at some voltage, every point connected to it by just wire is going to be at that same voltage. We just don't know what that voltage is yet. Because to figure out the delta V across R1, we're going to need to multiply current times resistance, and we don't know the current yet. So before we continue with any more voltage, let's figure out what the current is. Any other questions on this so far before we move on to finding the current?
Where you have it labeled as 0 volts, and then the other side is 98 volts, will it always be 0 on one side and then the full voltage on the other?
If you just have one battery, then yeah. And there's no reason this has to be called 0 volts. We could say this is, like, you could call this 1,000 volts. And then the battery would increase that by 98. So you'd have 1,098 volts. The important thing is the difference. It doesn't really matter what the voltage is. That's kind of arbitrary. What matters is the difference in voltage. So you could call this 1,000 volts and this 1,098 volts. You could call this 2 volts and 100 volts as long as the difference is 98. But it's usually most convenient to find the point that's going to have the point in the circuit that's going to have the lowest voltage of the whole thing, which is usually the point right before the battery or the negative terminal of the battery, and just label that 0 volts for simplicity, and then measure everything else from there. So as a general rule, when you're analyzing a circuit, I would start by just, I would start by figuring out what current, where do you have different currents? Label every different current based on the junctions with a variable. And then start labeling voltages, identify the region right before the negative terminal of the battery, the region on the negative side of the battery, and call that 0 volts. And then the positive terminal of the battery, that's going to be the high voltage region, specifically adding whatever the voltage of the battery is. And if there's several batteries in a row, you can generally just, as long as the batteries are in series, you can just add those together to treat them as one big battery. Any other questions on that so far? So let's see if we can deal with these resistors, because one way to find the current, instead of setting up some big system of equations, we could simplify this circuit until we just have one loop. Because if you just have one loop, the loop rule becomes much easier because there's only one current. So let's simplify things. R3 and R4, for instance, those together, how would we figure out if we want to treat them together as just one big resistor? How would we figure out what the resistance of that is? If we just want to treat R3 and R4 as one big resistor.
Would you just add them together?
Yeah, if resistors are in series, you can just add them. Yeah, the 7 plus 5 is going to give us 12 ohms. So let's call that R sub 3,4 is 12 ohms. That's the combined resistance. And the reason we can add those together, in series, you can just add the resistors together because they have to have the same current. So if you start writing out a loop rule equation, you're going to have delta V and delta V. So you're going to have negative I1 times 7 ohms plus negative I1 times 5 ohms. The series guarantees that it's the same current when you add the voltages together. And if it's the same current, what can you do algebraically if the same variable shows up, the same multiplier shows up in both terms?
Combine like terms.
Yeah, we can combine like terms. You could also even think of this as just factoring out the negative I1. Factor out negative I1, and what's left? Factor in I1 from the first term, we're left with just 7 ohms. Factor in negative I1 from the second term, we're left with just 5 ohms. So that's why we can just add those resistances together, because they have to have the same current, because that's the definition of series. Same current means you can factor that out, and then you're left with just resistance plus resistance. So this is why we have this very close tie between the idea of in series versus same current. I generally think of it as in series means they have to have the same current. And same current means that can be factored out. So you just add the resistances together, combining like terms. So that means R3 and R4 together act like a single 12 ohm resistor. And let's draw out the rest of the current, the rest of the circuit there. We've got this R2 that we haven't combined with anything yet. And also we've got R1 and R5. Even though they're on opposite sides of the battery, they're still on the same path, so they still have to have the same current. And therefore they're in series. So we can combine those and say together they act like what resistance? If you combine R1 and R5 in series, what would you do with the 3 ohms and the 2 ohms? Yeah, we can just add those together to get 5 ohms. So we can just say those together act like one big 5 ohm resistor. And it doesn't really matter which side of the battery we put it on, because in series is just added together, and adding together is commutative. The order doesn't matter. So we get this simplified circuit, or partially simplified anyway, where we've got, let's say we call this R15, which is 5 ohms. And we also have this R2, which we haven't modified yet, is still 8 ohms. And with that out of the way, with all these series resistors combined, are there any resistors, any pairs of resistors or combinations of resistors that seem like they're definitely in parallel? Yeah, R2 and R34 are in parallel because they both start at the same region and they both end at the same region. And I think it's easier to see this if we actually highlight those voltage zones. If you treat this as, here is some high voltage region, and then we go through a resistor and we get to a lower voltage region. But this entire zone is all the same voltage because it's all connected by wire. So this entire zone is all at the same voltage. And note that R2 and R34 both start at this voltage up here, and they both end at this voltage down here. R2 and R34 are just two paths that connect the same starting point to the same ending point. Because anything connected by wire can be treated as just the same point. So we know R2 and R34 are in parallel. And how can you combine resistances if they're in parallel?
Can't you do 1 over their resistance?
Yeah, we have to add the resistances in as reciprocals instead. 1 over this resistance plus 1 over this resistance. And the reason for that has more to do with the idea of adding currents. Previously, when we were looking at series, we were adding voltages based on the idea of the loop rule. But we can also look at this in terms of the junction rule, adding currents together. And if you're adding currents, we can go back to Ohm's law, the idea that delta V equals negative I times R. If you solve that for I, what would you get? How would you isolate I there? Yeah, delta V divided by R, and with a negative sign also. But that basically just signifies which direction we're going. So if you're adding currents, because in the loop rule, we're adding currents together. Like let's say we add current 1 plus current 2 to figure out what they combine to. If you add current 1 plus current 2, but then you replace each of those currents with negative delta V over R, you get negative delta V over R1 plus negative delta V over R2. And if they're in parallel, what do we know about the delta voltages? If they're in parallel, if both of those paths start at the same high voltage and both end at the same low voltage, what do you know about the delta V's if they're in parallel? Yeah, they got to be the same. This is one of the most important attributes of parallel. Series have to have the same current, but parallel have to have the same voltage, which means we can factor out that negative delta V, and we're left with 1 over R1 plus 1 over R2. So this is why in parallel, the resistances add reciprocally. They add 1 over the resistance plus 1 over the resistance. Because if we're adding currents, but current is delta V over R, and it's the same voltage, we can factor out voltage. We're left with 1 over resistance plus 1 over the other resistance. So that's what we're going to do here. We're going to add 1 over 8 plus 1 over 12. But that doesn't equal the total resistance. That equals 1 over the total resistance. So we can say 1 over R total, or R equivalent, equals 1 over 8 plus 1 over 12 to combine these together. And how do we add 1/8 plus 1/12? What's a common denominator?
Denominator.
Yeah, and what's that going to be here? What value would work as a denominator?
24.
Yeah, 24 is a number that's a multiple of 8 and a multiple of 12. So 1/8 we could multiply by 3 over 3 to get 3 over 24. 1/12 we could multiply by 2 over 2 to get 2 over 24. So that means 1 over the equivalent resistance is 5 over 24. And we're not quite done yet because that doesn't give us the equivalent resistance. It just gives us 1 over the equivalent resistance. So we take the inverse of both sides, raise both sides to the -1 power, and we get 24 over 5. Or in other words, 4 4/5 or 4.8 ohms. So these two resistors together, these two resistors in parallel, act like just one big 4.8 ohm resistor. Any questions on that so far? So let's combine those together. Let's just treat those as We'll just treat those as just one big 4.8 ohm resistor. And we'll call that R sub 234. So those together act like a 4.8 ohm resistor. And now how is that equivalent resistor combined with this other 1.5 resistor here? Yeah, we can just add those together because these are now in series. By simplifying that parallel network, that whole parallel blob is in series with the R15 resistor from earlier. In fact, we didn't really even need to combine 1 and 5 at the beginning. We could just say 1 and 5 are now in series with that R234. So we could just add 2 plus 3 plus 4.8 and get 9.8. So the total resistance of the whole thing is just 9.8. So we can now combine all of those together. We can say R total equals 9.8 ohms. The entire circuit acts like a 9.8 ohm resistor. And the nice thing about simplifying it is we now just have one loop. And one loop makes it much easier to do. We've got epsilon equals 9.8 volts. Sorry, 98 volts as the battery. If we now write out the loop rule is going to be much simpler. We know that the sum of all the delta voltages in the loop has to add up to 0. But what are the only things we go through if we pass around this loop? If you go around this loop, you're just passing through one battery and one resistor, right? So we just have delta V for that one battery plus delta V for that one resistor. Delta V for the battery is just epsilon, which is in this case 98 volts. Actually, let me write this out in terms of variables. We have epsilon. And what's delta V for any resistor? Yeah. So epsilon plus negative IR equals 0. And we can even solve that directly for current. If you isolate current here, what would you get? Yeah, add IR to both sides, divide both sides by R, we get epsilon over R. So that should be the current. Specifically, the current in this simplified loop is epsilon from the battery divided by the total resistance. And which current does that correspond to in the original circuit? Did we just find I0, I1, or I2? Yeah, that should be I0. Because the only thing we didn't simplify is the battery. Everything else we mushed together into one big resistor. But since the battery is the one piece we didn't simplify, didn't modify at all, the current we're finding is specifically the current through the battery. So that's what we've just found. Epsilon over R total is the current through the battery. So that's I sub 0. And this is a very useful shortcut. Once you've simplified the circuit, once you've combined all the resistors into just one big equivalent resistance, the current through the battery is just going to be epsilon from the battery divided by R total, just as an application of the loop rule to that simplified loop. And we have values for those. We know epsilon is 98 volts, R total is 9.8 ohms, divide those and we get 10 amps. So we now know the value of I0. I0, the current through the battery, is 10 amps. Any questions on that so far? And with that 10 amps, we know it's going to have to split up into I1 and I2. So we at least know I1 and I2 have to equal 10 amps. 10 amps equals I1 plus I2. But we don't know how it splits up yet. We don't know if it splits up evenly or more one way or the other. We do know we've got an 8 ohm resistor and a total of 12 ohms on this path. So which of those paths would you expect to get more current? Yeah, this left path here with the 8 ohm resistor. That's a weaker resistance, so we would expect more current on this path. And the one with more resistance is going to get less current. It's still going to get some current, just not as much. And they have to add up to 10 amps. To figure out how much, I find it helps to look at voltages here. So going back to the idea of voltage, we labeled this lower left corner as 0 volts, this upper left corner 98 volts because it gets a voltage boost from the battery. As we go through R1, we're going to lose some voltage. But we can now actually calculate how much voltage. What's the delta V for any resistor? If it's a resistor, we can calculate delta voltage as what? Yeah, negative IR. And most importantly, we have the current now. We know that the current through this resistor is 10 amps. That entire path gets 10 amps of current flowing through it. And we know the resistance is 3 ohms. So we can multiply those. 10 amps times 3 ohms is 30 volts. That means this resistor involves losing 30 volts. That way we would say that 30 volts is its voltage drop. So from one side of the resistor to the other, there's a decrease of 30 volts. 98 volts minus 30 volts is going to be 68 volts. So we know the voltage here is got to be 68 volts. So this T junction here, this region has to have a voltage of 68 volts. And if we know another voltage, we can figure out the current through this resistor. We don't know this voltage yet, but we can figure it out. Because what other resistor do we know the current through? What's the one other resistor where we know the current? Yeah, R5. We know the current is 10 amps. We know the resistance is 2 ohms. So we can calculate delta V. Once again, negative I times R. So 10 amps times 2 ohms would be negative 20 volts. So going through resistor 5 in the direction of current involves losing 20 volts. So if you start at some voltage and you lose 20 volts and you end up at 0, what voltage did you have to start at? What would this voltage have to be? Yeah, that's got to be 20, right? If you start at some unknown and you lose 20 and you end at 0, this had to have been 20. So we know this voltage is 20 volts. But it's not just the voltage at that one point, because any point connected by just wire has to have the same voltage. So it's really not just this point here, but all the points connected to it by just wire. This entire shaded in region is all at the same voltage. Any points connected by just wire are sharing the same voltage. And the important thing about that is we now know the voltage difference across resistor 2. What's the difference in voltage from right before resistor 2 to right after resistor 2? Yeah, it's losing 48 volts, right? Because we have 68 volts at the top and 20 volts at the bottom. The difference between those is 48. So we can say that for resistor number 2, the delta voltage is going to be negative I times R as usual. The delta voltage from start to finish is negative 48. And you can even look at that as final minus initial. Final is 20 volts, initial was 68 volts. 20 minus 68 is negative 48. So negative 48 volts equals negative I2, which is still unknown, times the resistance, which is 8 ohms. So with that, how would you solve for I2? How could you isolate I2 in that equation? Yeah, divide the voltage by the resistance. Divide both sides by negative 8 in this case. The negatives cancel out. 48 volts over 8 ohms is going to be 6 amps. So we now know that current 2 must be 6 amps. Any questions on that so far? And we could do the same thing for resistors, really for resistors 3 and 4 together. At this point, it might be useful to treat resistors 3 and 4 as still combined. So if you treat path 3, 4, the path consisting of resistors 3 and 4, we can still use delta V equals negative I times R. The voltage drop, we're still going from 68 volts at the beginning to 20 volts at the end. So delta V is still negative 48 volts equals negative I1 times, and what's the total voltage or total resistance of this entire path? Yeah, 12 ohms. So to get I1, we can just divide both sides by negative 12 and get 48 volts over 12 ohms, which is 4 amps. So that's the current in this entire path, the path consisting of resistors 3 and 4. And as one final check, note that I1 and I2, 6 amps plus 4 amps, does add up to 10 amps. So this confirms the junction rule. The 4 amps and 6 amps merge together to get 10 amps. Also, as we predicted, the lower resistance path has more current, the higher resistance path has less current. In fact, they're proportional. 12 amps is 1.5 times as much as 8 amps, or sorry, 12 ohms is 1.5 times as much as 8 ohms. And likewise, 6 amps is 1.5 times as much as 4 amps. So the ratios remain the same. Any other questions on that? And one last thing we could do if we needed to would even be to find the voltage at this corner. And for that, you could go from either direction. You could start at 68 and subtract 7 times 4, because that's how much voltage you're losing. Or you could start at 20 and backtrack by adding 5 times 4. Either way would get you to 40 volts here. So this corner would be 40 volts. And at that point, you know every current in all the paths. You know the voltage at every so the voltage at every location, the current in every path. That's everything you need to know about the circuit. You could then, for instance, if you wanted to know the power output of any of these resistors, you could now use any of the power formulas because you know everything about each one of those resistors. Any other questions on that?